Factoring by grouping. So anything can be a factor as long as each term of the polynomial can be divided by it. And that includes binomials. So looking at this example below, we have this polynomial expression, and what we see is that each term, so again, here's one term of our expression, and here's the other term of our expression because they're separated by a plus or minus sign, in this case a minus sign. And each term has a binomial that is identical. So each term could be divided cleanly by x plus 2. So I can factor x plus 2 off of each term, leaving me with 3x, so 3x times x plus 2. If I was to divide that by x plus 2, I'd be left with just 3x. And if I did the same thing, divided the other term by x plus 2, I'd be left with just negative 7. So I can factor off, I have essentially pulled x plus 2 off of each term by dividing it. Just like we did before, except now we're doing it with a binomial, but the rules are the same. Sometimes we'll see examples where it looks like the binomials are close, but they're not quite right. But this expression is still factorable because negative y minus 5 and 5 minus y are just opposites of each other. Y minus 5 is equal to negative 5 minus y. And I'll show you what happens if we multiply that negative in to each term. We get negative 5 plus y rearranged is y minus 5. So if you see brackets that are opposite of each other by a sign, what we're going to do is factor out a negative 1. So imagine dividing each term by negative 1, and then we bring it out front. So I have 5y times y minus 5, that's the first term. And then I pull that negative 1 out, and so it turns my second term into negative 3. So that's where the negative 1 went. It went into turning positive 3 into negative 3. And then negative 5 plus y, or, again, rearranged, that would be y minus 5. And now I have these common brackets for each term, and so I can factor the common brackets off each term, and I'll get y minus 5. So that's what I've factored off, and I'm left with 5y minus 3.
So in this example, we again see something similar between the factors that are in the brackets. They're just different by negative sign. Not the negative sign that's in the front here, but by the fact that the 6p is positive on the left factor and negative in the right factor, whereas the 5 is negative in the left factor, but now it's positive in the brackets on the right factor. So we're going to start by taking a negative sign out of the right-hand factor because we always like our variable terms to be positive. So we've got our 2p, and we have 6p minus 5 still. We got this same negative sign, and now I'm taking out a negative 1 from here. And that basically means I have a minus 5 in here now, but a positive 6p. So if we tidy that up a bit, we have our 2p, 6p minus 5 again. And now when we minus negative 1, that's just like adding 1. So this just turns into a plus sign. And here, let's rewrite these terms in order with the positive variable term first, 6p, and the constant term minus 5 second. Now if we look at these two larger factors, we see that 2p, 6p minus 5, and 6p minus 5 have 6p minus 5 in common. So we're going to take out 6p minus 5. And that leaves 2p from the first term, the first factor. And when we pull 6p minus 5 out of 6p minus 5, we're not left with 0, we're left with 1. Because 6p minus 5 times 1, if you were to expand that back in, would bring you back to 6p minus 5.
Now can we do the same thing with this example? So I have 10m times m plus 1 minus m minus 1. Well, those two brackets sort of look like opposites of each other. What would happen if I factored out that negative 1? So I pull negative 1 off of each term. Well, I'd get 10m times m plus 1, and then those pulling off a negative 1 from each term would mean I have minus negative 1 or plus 1, and then I would have negative m plus 1 in the brackets. Ooh, but this, you can see, is not the same as the other bracket. So these are not common factors of our two terms. There's no factoring I can do. So what I just really wanted to show you was that what really matters is that both items in the binomial, it matters that both of those things, both pieces of the binomial, have opposite signs of one another. Here, the m's had the same sign to start with, so these aren't true opposites of each other like the last example. So this skill that we just covered there is an important part of a type of factoring called factoring by grouping. And this is a method of factoring that might work if we have 4 terms of a polynomial. So if we look at the example here, xy plus 3y plus 2x plus 6, do these 4 terms have anything in common? Can we factor off a common factor? And the answer is no. Each of those 4 terms does not have something in common. They don't have a common coefficient, and they don't have a common letter or variable. So there's nothing that we can do to factor off of every term. However, look at the pairs of terms, and we might realize that there is some factoring we can do in pairs. So this is called grouping, and now we're going to factor each group. So in this first group, I can factor off a y, and I'm left with x plus 3. And in the second group, I can factor off 2, and it's going to be a positive 2 that I'm going to factor off. So this plus has to be here. That's very important because it's separating the 2 terms. So I'm left with x plus 3 in the second brackets. And now we notice that we have common factors of x plus 3. So I can factor off x plus 3 from each of those 2 terms now, and I'm left with x plus 3 times y plus 2. And so that's called factoring by grouping. Even though I had 4 terms with no common factors, by factoring the pairs of each the pairs of each group, I was able to factor the expression. So I'm going to run through a couple more examples of factoring by grouping. So here's my pairs. Now it's important that this negative be here in the second group. Always keep the signs there. But I'm separating these groups by a plus sign. So I'm going to do my first factoring here of x squared and 3x. What do they have in common? Well, they have an x, and I'm left with x plus 3. And then I'm going to separate these pairs by a plus, and I'm going to really include that negative sign in the second pairing. So I'm going to factor it out of the second pairing. So I have negative 2 in common of that second pair, and I am left with x plus 3. Now the reason why I wanted to factor off the negative was because if I didn't factor off the negative, I would have had plus 2 negative x minus 3. And then my brackets wouldn't be the same for each term. I wouldn't have the same binomial on each term. So it's important to watch your negative signs and see how they can help you factor. So I've factored that negative 2 off the second pair. So now I have x times x plus 3 minus 2 x plus 3, and I can factor off that x plus 3 term. And I'm left with x plus 3 times x minus 2. And here's another example. So this time we're going to find that we're going to increase the complexity a little bit. And so this first pair I have, what can I factor off each term? I can factor off 3x, each pair, and I'm left with 2x minus, and 3x, remember when factoring it's like pulling off with division, so it's divided by 3x from each term. Well, 3x divided by 3x is 1, so it's really important that I keep that 1 in the bracket. And then in the second pair, so I'm going to separate the two pairs with a plus sign, I'm going to factor off negative 2. And again, I'm using the negatives to my advantage. So I'm going to factor off negative 2 from each of those pairs, items in the pair. And I'm left with, so the reason I wanted to do that was because dividing by negative 2 changes the sign of that first term in the pair. So now I have 2x, and then 2 divided by negative 2 is negative 1, and now I've done the thing again where I have the same binomial on each term. So I'm using that negative sign to my advantage so that I can completely factor this expression. Lastly, factoring by grouping. So let's see what we can do here with these pairs. So here's my first pair, here's my second pair. So for the first pair, all I can do is factor off an r, 7r plus 9. And on the second pair, it looks like I can factor off 5t. So I have plus 5t, and that leaves me with r plus 3. Oh, but look, these two binomials that were left off when we factored by grouping, there's nothing in common. The binomials are not the same. So this is not factorable. And so that's why at the very, very start of this video, I said that factoring by grouping might help us factor expressions with 4 terms, but it's not guaranteed. Of course, there are expressions out there that are not factorable by this method, and I've just shown you an example of one of them. But you're not going to encounter very many of those, but I just want you to be aware that sometimes an expression might not be factorable this way.